6 eruptions in under 10 hours. That is what a single small island in the middle of the Sunda Strait did in one morning, and the people who watched this volcano for a living did not shrug it off. They raised the alarm, they widened the danger zone, and they told the fishermen and the boats to stay back. Because this is not one puff of smoke and then silence. The ash is turning black. The ground beneath the island is humming without pause, and this exact volcano has done something before that killed hundreds of people who never felt a single warning on an ordinary night with no earthquake and no time to run. So the real question is not whether it is erupting. It is what the island itself might be about to do. Before we get into it, if you enjoy what we do here at Project Nightwatch, hit that like button and subscribe so you never miss any of our nightly debriefs. And do me a favour, drop a comment and tell me where in the world you're watching from tonight. Now let's get into it. Part 1. 6 eruptions before lunch. 6 times in under 10 hours. That is how many times a small island in the middle of the Sunda Strait blew ash into the sky on the 8th of July, 2026. And the people who watched this volcano for a living did not shrug it off. They raised the stakes, because this is not one puff from a crater followed by silence. This is a volcano that is intensifying, hour by hour, in front of instruments that can hear it breathing. You almost certainly know the name Krakatoa. It is one of those words that carries its own weight, even if you have never read a single page about it. What is happening right now is happening at the volcano that grew up inside the wound Krakatoa left behind. Its name is Anak Krakatau, which means, quite literally, the Child of Krakatoa. And over the first 2 weeks of July, the child has been throwing a very serious fit. We have been dealing with this volcano for a while now. It has been on the watch list, stirring, testing, sending up signals that something inside it was changing. And the whole time, the message from the people who study it has been the same. Watch for any increase in activity. If the tempo picks up, if the eruptions start stacking up, that is the thing that should get your attention. Well, right now, the tempo has picked up. The eruptions are stacking up. This is precisely the development we were told to watch for, arriving in real time. So the question is not whether something is happening. Something is clearly happening. The question is what that something means, and how far it might go. Let me walk you through that one day, because the sequence tells you almost everything you need to know about why this matters. The first eruption came just after midnight, around 11 minutes past 12 in the morning local time. Visibility was poor, so nobody could get a clean look at the ash column in the dark. But the volcano does not need daylight to be recorded. The seismograph caught the blast anyway, a volcanic signal with a maximum amplitude of 24 millimeters, lasting about 40 seconds. That is the machine equivalent of the ground flinching, and notice something in that very first data point. The volcano erupted in the dark, when no human eye could confirm it, and the record captured it anyway. This is important, because it means our picture of that day is not built on what happened to be visible. It is built on a continuous instrumental log that does not sleep, does not blink, and does not need daylight. When we say 6 eruptions, we are not counting the ones somebody happened to photograph. We are counting what the ground itself registered, whether or not anyone was looking. That is a far more complete and far more trustworthy record than eyewitness accounts alone, and it is why the escalation can be stated as fact rather than impression. Then the volcano kept going. At 10 minutes to 6 in the morning, grey to black ash rose about 250 metres above the summit. In feet, that is a little over 800, roughly the height of a 60-storey building, standing on top of an island that is itself the tip of a mountain rising out of deep water. That eruption lasted about 44 seconds, and the seismic amplitude ticked up to 26.1 millimeters, a little stronger than the one before it. Then, at 11 minutes past 7, another ash column climbed to about the same height and drifted off to the northwest. But this time the seismic signal was noticeably stronger, 44.4 millimeters, nearly double the amplitude of the midnight blast. If you're keeping track, and the scientists absolutely are, the trend line is not pointing down. Then came another at 42 minutes past 8 in the morning, a thick black column. Then one at around 35 minutes past 9, then another at 54 minutes past 9. 6 eruptive pulses before most of us would have finished our second cup of coffee. Let me put those 6 pulses in a row so you can feel the rhythm of them, because the rhythm is the point. Midnight, a signal in the dark. 10 minutes to 6, grey to black ash. 250 meters, 44 seconds, amplitude climbing. 11 minutes past 7, another 250-metre column drifting northwest. The seismic signal now the strongest yet at 44.4 millimetres. 42 minutes past 8, a thick black column reaching about 100 metres above the crater, logged for roughly 40 seconds, the dense black ash pushing off to the northwest again. Then 35 minutes past 9, then 54 minutes past 9, the gaps between them shrinking, the volcano barely pausing to breathe. In under 10 hours, this island detonated 6 times, and the machines never once caught it going quiet in between. And I want you to understand why the frequency specifically is such a strong signal, more than the height of any single column. A volcano that produces one modest eruption and then rests is releasing pressure and returning toward equilibrium. A volcano that fires again and again, with the gaps between blasts staying short, is one where the supply of gas and magma is outpacing the volcano's ability to vent it. The pressure is not being relieved by the eruptions. It is being replenished faster than the eruptions can spend it. That is why frequency, not just size, is what makes experienced observers uneasy. 6 in a morning is not 6 times as bad as 1. It is a categorically different signal, because it points to a source that is being actively and continuously driven from below. Now, compare that to where this same volcano was just a couple of weeks earlier, because the contrast is the whole story. In the last days of June, Anak Krakatau was already stirring. It was pushing out a grey-white plume only about 100 metres above the crater, drifting off to the southwest. It was serious enough to watch, serious enough that it was held at alert level 2, the level they call Waspada, with a 2-kilometre exclusion zone. That was the opening chapter. If you have followed this volcano with me before, you saw that reactivation take shape, the slow build of shallow earthquakes, the crater warming up, the first grey ash. Back then it was a warning that something was waking up. What has happened since is that the something woke all the way up. In the span of about 2 weeks, the alert has been raised a full step from level 2 to level 3. The exclusion zone has grown from 2 kilometres to 3, and the plume has gone from a single 100-metre puff of grey-white to clustered black columns 2.5 times as tall, erupting 6 times in a single morning. That is not the same volcano behaving the same way. That is a clear, measurable escalation from one phase to a more dangerous one. That is escalation. And here is the part that separates a person who is genuinely worried from a person who is just counting fireworks. It is not only the number of eruptions that matters, it is what the volcano was doing in between them and what it was doing before them. Because the answer is that it never really stopped. It was not resting between blasts. It was charging, shaking, venting, and releasing ash the whole time. The eruptions were not 6 separate events. They were 6 visible spikes on top of a system that was humming continuously the entire day. Now, why does that get people out of their chairs? To answer that, you have to understand what kind of volcano this is and what it has already done once before on a night that nobody who lived through it will ever forget. Because the danger here is not really the ash. The ash is the volcano telling you it is awake. The thing you actually have to watch is the island itself. And to understand why the island is the danger, we first have to listen to what the ground is saying in a language most people have never been taught to read. Part 2. The sound of a system under pressure. The most important number from that day is not the height of any ash column. It is a word that sounds almost boring until you understand it. Tremor. When we talk about a volcano shaking, most people picture a single crack, one sharp jolt, an earthquake with a beginning, a middle, and an end. That is not what has been happening at Anak Krakatau. What the instruments have been recording is something more continuous, and in some ways more unsettling. The volcano has been showing intense, sustained volcanic tremor. Not tectonic tremor, the kind you get when 2 slabs of rock grind past each other. Volcanic tremor, the whole system vibrating at once. Here is a way to feel what that means. Think about a water pipe in your house. When the pipe is empty and still, it is silent. The moment you open the valve and force water to rush through it, the pipe starts to hum and shudder. You can put your hand on it and feel it vibrating, because something under pressure is moving through a confined space. That is volcanic tremor. It is not one isolated snap. It is the sound of gas, magma, and pressurized fluid pushing their way up through the volcano's internal plumbing. And when that hum does not stop, it means the pressure is not releasing all at once. It is sustained. The system is loaded. Scientists do not just listen for one kind of signal, they sort the shaking into categories, and each category is a clue about what is physically happening underground. On a representative day during this phase, the tally looks something like this: 5 eruption earthquakes, 10 emission events, 2 harmonic tremor events, 1 low-frequency event, 13 hybrid or multiphase events, 1 shallow volcanic earthquake, and 4 continuous tremor signals. To an untrained ear, that is just a list. To a volcanologist, it is a diagnosis. Let me translate the important ones. Hybrid events, those multiphase signals, point to 2 things happening together: rock physically cracking and fluid moving through the cracks at the same time. Low-frequency events are the fingerprint of gas, magma, or pressurized fluid on the move inside the volcano, not solid rock breaking, but something flowing. Harmonic tremor means the whole system has settled into a sustained resonance, like a note being held rather than a drum being struck once. And continuous tremor, the fact that it just keeps going, tells you the volcano is not calming down between the eruptions. It is staying pressurized. And notice that these are not a scientist's subjective impressions. They are categories defined by the physical shape of the signal on the record, the frequency content, the way the energy rises and falls, the duration. A trained analyst looking at the seismogram can tell a hybrid event from a low-frequency event, from a simple eruption quake, the way a doctor can read different arrhythmias off an electrocardiogram. That objectivity matters because it means the picture of a pressurized, fluid-driven, shallow system is not a matter of interpretation or mood. It is written into the data itself. Anyone qualified, looking at the same records, would read the same story. Put those together, and you get the picture of an active, shallow, pressurized system, not a volcano running out of steam, a volcano that is being actively fed from below. This is why we call the internal structure a plumbing system in the first place, because magma and gas travel through it the way water travels through pipes, and right now those pipes are full and under pressure. Let me slow down on the difference between the 2 families of shaking, because it is genuinely the key to reading this volcano, and once you have it, you will never look at a headline about volcanic earthquakes the same way. A tectonic earthquake is brittle failure. It is rock that has been bent and loaded by stress until it suddenly snaps along a fault, releasing that energy in a sharp, high-frequency burst, a crack. You get a distinct beginning and a distinct end. Volcanic tremor is not that. It is not one rock breaking. It is the continuous jostling of the whole edifice by fluids in motion, magma and gas and superheated water, forcing their way through cracks and conduits, and the frequencies involved are lower, more drawn out, more like a groan than a crack. When a monitoring team sees the record fill up with that low, sustained signal instead of a few sharp spikes, they are not looking at rock breaking under old stress. They are looking at fresh material on the move. Now let me give you a little more on those specific signal types from the daily tally, because each one is a different window into the same underground process. Emission events are the tremor bursts associated with gas nash actually being pushed out of the vent, the seismic fingerprint of the volcano exhaling. Shallow volcanic earthquakes tell you the activity is happening near the surface, close to the crater, not miles down, which matters enormously because a shallow pressurized system is one that can reach the surface quickly. And the specific mix on that representative day: 5 eruption earthquakes, 10 emission events, 2 harmonic tremor events, 1 low-frequency event, 13 hybrid events, 1 shallow volcanic earthquake, and 4 continuous tremor signals, is not a random assortment. It is dominated by the signatures of fluid movement and shallow pressure. 13 hybrid events in a single day is a lot. Each one is a small drama in which rock cracks and, in the same instant, fluid rushes into the new opening. Picture magma forcing its way upward, prying open new fractures as it climbs, and gas rushing through those fresh cracks the moment they appear. Each hybrid event is one of those moments captured on the record, a tiny report from deep inside the volcano saying, the path just widened, the fluid just moved. 13 of them in a day paints a picture of a system that is not static, not waiting, but actively rearranging its own insides to let more material up. That is a system actively remaking its own internal plumbing to accommodate rising magma. The word shallow deserves its own moment, because it changes the timeline of everything. When the earthquakes and tremor are happening close to the surface, it means the action is not buried tens of kilometers down where it would take a long time to reach the crater. It is near the top. Magma and gas that are already high in the edifice can break through with very little delay. A deep system gives you a longer runway, more time between the first stirrings and any surface expression. A shallow one collapses that runway. The pressure is already close to the exit, and that is exactly what we are seeing. Activity concentrated near the surface, expressing itself as frequent eruptions rather than as deep rumbles that never quite arrive. It is one more line in the same paragraph. Active, shallow, pressurized, fast to the surface. None of those words individually is alarming, but stacked together they describe a volcano that can act quickly and has been doing so. There is one more thing this sustained tremor tells us, and it is the connection that makes the whole picture cohere. A volcano that erupts once and then falls silent is a volcano that has released its pressure. The valve opened, the steam escaped, the system relaxed. That is not what Anak Krakatau has been doing. The continuous tremor between the eruptions is the tell that the pressure never fully released. Each of those 6 blasts vented some of it, yes, but the underlying source kept pushing, kept resupplying, kept the pipes full. That is why the eruptions clustered instead of resolving. The system was being refilled faster than the eruptions could empty it, and this is the crucial connection back to those 6 eruptions. The blasts you can see are just the moments when the pressure finds a way out. The tremor you cannot see is the pressure itself, and it has been there the whole time, in the gaps, in the quiet stretches, in the middle of the night. There is a reason this matters so much for a volcano with Anak Krakatau's specific history. Sustained tremor is not just a sign that an eruption might be coming. It is a sign that the edifice is being continuously shaken and continuously loaded from within. Every hour that the tremor runs, magma and gas are working through the cone, and the cone is being jostled by its own internal activity. On a stable, old, well-built mountain, that jostling is absorbed. On a young, loose, waterlogged island cone perched over deep water, sustained shaking is one of the things that can help nudge an already marginal slope toward failure. So the tremor is doing double duty in this story. It is the vital sign that tells us the volcano is alive and active, and it is, potentially, part of the mechanism that could destabilize the very flank we are most worried about. The same signal that says the system is charged also says the system is being physically worked. I want to be careful not to overstate that. Tremor by itself does not mean a collapse is coming, and volcanoes produce long stretches of tremor without ever shedding a flank. But you asked, in a sense, what is happening here? And the honest answer is that the ground beneath this island has been in a state of near continuous agitation, punctuated by explosions, for days. When a person watches this volcano and says the activity has increased, and we need to pay attention, this is what they are reading. Not the drama of a single explosion, the steady humming evidence that the system underneath is charged and moving. But a charged system still has to express itself somehow, and the way it does that is through the crater. In a plume you can actually see with your own eyes, and it turns out the colour of that plume, the simple question of whether it is white or grey or black, is one of the most honest signals this volcano gives us. So let us look up at the column, because it has been changing colour in a way that tells its own story. Part 3. When the smoke turns black. There is a detail in the reports from these eruptions that is easy to skim past, and it is one of the most useful things you can learn about reading a volcano: the colour of the ash. Over this sequence, observers described the crater smoke as white, then grey, then black, with intensity ranging from thin to thick, rising up to about 250 metres above the summit. Now most of us look at a volcano and see smoke as smoke, but those 3 colours are 3 completely different messages, and the volcano is not being poetic when it changes from one to the next. It is telling you exactly how violent the process underneath has become. White is mostly steam. When a volcano puffs out a white plume, it is largely water vapour, gas escaping, the system breathing. A volcano can sit there breathing out white steam for a very long time without ever erupting strongly. It is the equivalent of a kettle venting. Not nothing, but not an explosion either. Grey is the middle warning. Grey means ash is now mixing into that steam. Fragmented material is starting to come up with the gas. The system is no longer just exhaling, it is starting to bring pieces of itself along for the ride, and then there is black. Black ash is the one that makes people lean in. Black means dense ash, fresh fragmented rock, the product of stronger explosive bursts tearing new material out of the throat of the volcano. When the plume goes black, The system is not breathing anymore. It is blasting. It is ripping rock apart and firing it out of the crater. And on the 8th of July, the columns were reaching grey to black. Thick black ash was recorded moving off to the northwest. That is not a kettle venting. That is a volcano in an explosive mood. There is a reason this simple colour rule is so useful, and it comes down to what is physically leaving the crater. Steam carries no rock, just gas that has separated from the magma and escaped. When you start seeing grey, it means the escaping gas is now dragging fine ash up with it, which means fragmentation is occurring, magma being torn into small pieces by rapidly expanding gas. Black is the extreme of that same process, so much fresh, dense, newly shattered rock coming up that the plume loses its lightness entirely. So the colour is really a readout of how violently the magma is being fragmented down in the throat of the volcano. A quiet system releases gas and stays pale. A violent one shreds rock and goes dark, and it does not require any special instrument to read. Anyone standing on a passing boat or watching a clear satellite image can see the difference between a white plume and a black one. It is one of the few volcanic warning signs that is visible to the naked eye, which is part of why observers pay such close attention to it. And the direction of drift matters too, not just the colour. During this sequence, much of the ash was pushed to the northwest, and at times to the southwest out over the strait. Ash is not a neutral thing to have raining down on a populated region. The fine particles are hard on the lungs, especially for children, the elderly, and anyone with a respiratory condition. They coat crops and contaminate open water supplies. They reduce visibility on the water, which is a real hazard in a strait full of small boats. So even setting aside the dramatic collapse scenario, a volcano throwing repeated ash columns across a busy waterway is already imposing a real cost on the communities downwind, which is part of why the authorities take the exclusion zone and the advisories so seriously. This is not a remote peak dusting an empty wilderness. Whatever comes out of this crater drifts toward people, and the shifting wind direction over these days, sometimes northwest, sometimes southwest, means that different communities and different stretches of the shipping lane take their turn under the plume as the pattern changes. There is no single safe direction to stand. The ash goes where the wind sends it, and in this crowded strait the wind is always sending it somewhere inhabited. Here is the elegant part. That colour progression, white to grey to black, lined up almost perfectly with the seismic amplitudes climbing through the day, from 24 millimeters at midnight up toward 44 millimeters by mid-morning. Two completely independent instruments, one measuring what your eyes see in the sky, and one measuring what the ground feels, telling the same story at the same time. The system is intensifying. When two different measurements agree, you pay attention. Now, I want to address something that could confuse you if you were following the raw reports, because at first it looks like a contradiction. On one hand, people standing near the island and watching the crater reported relatively low plume heights, sometimes only tens to a couple hundred meters above the summit. On the other hand, aviation and satellite monitoring watching from space showed ash spreading out at altitude over the strait. The Darwin Volcanic Ash Advisory Center, using imagery from the Himawari 9 weather satellite, at one point placed ash as high as flight level 050, that is around 15,000 feet, roughly 4,600 meters. Later advisories showed continuing ash at a lower altitude, around flight level 030, about 3,000 feet, drifting mainly to the southwest. So which is it? Low or 15,000 feet? The answer is both, and understanding why is important. It does not mean one source is wrong or lying. It means different instruments are measuring different parts of the same ash cloud at different moments. A person standing on the ground reports what is visible directly over the crater right now. A satellite advisory detects the ash cloud after it has spread out and drifted away from the volcano, sometimes catching a taller, older plume that has already travelled downwind. The volcano is not producing one neat column. It is producing a messy, evolving cloud, and each tool sees a different slice of it. It is worth understanding why there is a whole system, staffed and running around the clock, dedicated to tracking volcanic ash from space, because it tells you that this is not just an academic exercise. The Darwin Volcanic Ash Advisory Center is one of 9 such centers around the world, and its job is to warn aviation. Volcanic ash is not like the soft ash from a campfire. It is finely fragmented rock and glass, abrasive and hard, and when a jet flies through an ash cloud, that material gets sucked into the engines where temperatures are high enough to melt it. It solidifies on the turbine blades, chokes the engine, and can shut it down entirely in flight. There are documented cases of airliners losing all engines after flying into an ash cloud they could not see at night. So when the Darwin Center, using the Himawari 9 geostationary satellite parked over the Western Pacific, detects Anak Krakatau's ash climbing to flight level 050, about 15,000 feet, and issues an advisory that is a live warning to every aircraft in the region to reroute. When later advisories bring the ash down to flight level 030, roughly 3,000 feet, and note it drifting to the southwest, they are tracking a moving hazard across one of the busier corners of Southeast Asian airspace. And this is exactly why the ground and satellite views can look so different and both be right. The satellite is not trying to measure the plume standing over the crater. It is tracking the ash cloud as a spreading, drifting hazard, catching it where it is thickest and highest, sometimes a plume that was thrown up an hour earlier and has since travelled out over the strait. The ground observer, meanwhile, is reporting the live column at the vent in that specific moment, which might be a modest few hundred metres even as an older, taller cloud is still spreading downwind at altitude. Two honest observations, two different parts of the same evolving cloud, two different clocks. Once you understand that, the apparent contradiction dissolves, and what is left is a single coherent fact. But when you put the ground reports and the satellite data together, the conclusion is not fuzzy at all. It is clear. Anak Krakatau is still erupting, and I want to stress how durable that conclusion is, because it survives every apparent disagreement in the raw numbers. Whether a given observer logged the plume at 50 metres or a satellite caught it at 15,000 feet, whether one report said grey and another said black, whether one advisory placed the ash at flight level 050 and the next at 030, the common thread through all of it is that material was coming out of this volcano across multiple days. The activity did not stop on the 9th, it did not stop on the 10th. The Darwin Center kept issuing advisories, the seismographs kept logging events. Every independent stream of information, however much they differed on the details, agreed on the headline. This volcano is in an active eruptive phase, and it did not switch off after that 6 eruption morning. It has been holding at alert level 3 out of 4, the level they call Siaga, and I want to be precise about what that means, because it is the official system telling you how seriously to take this. Level 3 is the second highest tier in Indonesia's 4-level volcanic alert scale. It is not the maximum, but it means the volcano has entered a more serious phase, with increased eruptive activity and a heightened danger zone around the crater, and it comes with a hard boundary drawn on the water, an exclusion zone that tells you a great deal about what the authorities are actually worried about. That boundary, and the reason it exists, is where this story stops being about a plume of smoke and starts being about something far more dangerous. Part 4. The island is the volcano. The exclusion zone around Anak Krakatau is now 3 kilometres from the active crater, almost 2 miles. Residents, tourists, fishermen and boats are all being told to stay out, and I want to be clear that this restriction is not decoration. It is not a formality. When they draw that circle on the water, they mean it, because the danger near this particular island can change faster than almost anywhere else on Earth. To understand why, you have to understand what Anak Krakatau physically is, and the key fact, the one that changes everything, is deceptively simple. This is an island volcano. The island is the volcano. There is no separation between the mountain and the sea. The mountain rises directly out of the water and the water is deep. Now compare that to a volcano on land. When a volcano erupts on solid ground, the main threats are the ones you would expect. Ashfall that blankets everything. Lava flows. Pyroclastic flows. Those fast-moving avalanches of superheated gas and rock. Volcanic bombs hurled from the crater. Toxic gas. Mud flows called lahars when ash mixes with water. That is already a fearsome list, and Anak Krakatau has every single item on it. Let me make that list concrete for a moment, because the phrase "the usual hazards" can wash right over you. When Level 3 was declared, the agency specifically flagged the potential for hot clouds, for lava, for incandescent ejecta, and for heavy ashfall. Hot clouds is the plain language name for pyroclastic flows, and they are among the most lethal things a volcano produces. A pyroclastic flow is an avalanche of superheated gas, ash and rock fragments that pours down the flank of a volcano at speeds that can exceed 100 kilometers an hour, with internal temperatures that can run into the hundreds of degrees. You cannot outrun one. Incandescent ejecta means glowing chunks of molten rock, volcanic bombs, flung from the crater and landing far down the slopes. Heavy ashfall can collapse roofs, foul water, and mixed with rain, form lahars, fast-moving slurries of ash and water with the consistency and destructive force of wet concrete. And these are not gentle hazards that give you time to stroll away. A pyroclastic flow can descend a flank faster than a car drives on a highway, and the superheated gas within it kills instantly, long before the visible cloud even reaches you. Volcanic bombs can be flung well beyond the crater rim, arriving without warning as glowing projectiles the size of cars. Even the ashfall, which sounds almost benign compared to lava, is deceptively dangerous, because wet ash is heavy, and enough of it accumulating on a roof can bring the whole structure down on the people sheltering inside. This is why an exclusion zone is drawn as a hard circle and enforced. It is not that danger becomes likely at 3 kilometers and impossible at 3.1. It is that these hazards are fast, lethal, and unpredictable in their exact reach, so the only safe policy is distance, and generous distance at that. Every one of those is on the menu at Anak Krakatau, which is exactly why the crater and its immediate surroundings are off limits. And it is worth pausing on how strange it is that a volcano can be both of these things at once. On any ordinary day, even an active one, Anak Krakatau's threats are local. Stay off the island, keep your boat outside the exclusion zone, and the ashfall, the bombs, the pyroclastic flows all stay within a manageable radius of the crater. In that sense, it behaves like a well-understood bounded hazard. But the island volcano's extra failure mode does not respect that radius at all. A flank collapse could send a wave far beyond any exclusion zone, onto coasts kilometers away that felt perfectly safe. So this is a volcano with two completely different danger scales stacked inside it. A near-field scale, measured in the couple of kilometers around the crater, that governs the everyday eruptive hazards, and a far-field scale measured across the whole strait that only activates if the island sheds part of itself into the sea. The exclusion zone protects you from the first. Almost nothing protects a distant coast from the second except the volcano choosing not to collapse, so the land-based hazards alone would justify keeping people away. But here is the thing that elevates this specific volcano into a different category of danger. But because it is an island volcano sitting in deep water, it has one more hazard that a land volcano simply cannot have: slope failure into the sea. And this is the one that keeps volcanologists awake at night. It is the hazard that turns a local eruption into a regional disaster, that reaches beyond the crater and beyond the exclusion zone and out to coastlines that never felt a thing. And it is the hazard this specific volcano is most famous for, because it is the one it has already used on more than one occasion to kill. Here is the mechanism, and it is important to sit with it. When a volcano like this erupts repeatedly, the cone keeps building. It piles up new material, layer after layer of fresh, loose volcanic rock and ash. But that material is not neatly cemented into a stable mountain. It is stacked, fast and messy, on the steep flank of an island that drops away into deep water on every side. So the cone grows, and as it grows, it can become unstable. And an unstable pile of volcanic material perched over deep water has one very dangerous thing it can do. It can collapse. Think about the geometry for a second, because it is genuinely precarious. A cone growing on land can slump and spread out sideways onto more land. There is somewhere for the material to go, and the failure tends to be gradual. But a cone growing on a small island is building on a platform that drops away steeply into deep water on every side. The strait around the volcano is deep, hundreds of meters in places, so the fresh material piling up on the flanks is not resting on a broad, stable base. It is stacking up on the rim of an underwater cliff. Add to that the fact that this material is hot, water-saturated in places, riddled with gas, and being constantly jolted by the very eruptions that are building it, and you have a structure that is being assembled quickly and badly right at the edge of a drop. Gravity is patient. It only has to win once, and we know exactly what happens when a large mass of that material suddenly slides into the ocean. The water has to go somewhere. When you displace an enormous volume of water in an instant, you get a wave. You get a tsunami. Not the kind triggered by an earthquake far out at sea, but one born from the volcano itself, from a piece of the mountain falling into the water. And the reason this is so much more dangerous at an island than at, say, a lakeside cliff, comes down to the depth of the water and the speed of the failure. When a large mass drops into deep water quickly, it transfers an enormous amount of energy to the sea almost instantly. The water does not simply ripple, it heaves. It piles up into a wave that then races outward. In the open, deep water of the strait, that wave can travel fast, and because it starts close to shore, it does not have far to go before it arrives. There is very little distance to buy time. A wave born at a volcano in the middle of a strait can be onto the nearest coast before anyone even understands that a collapse has occurred. The proximity that makes the Sunda Strait so scenic and so economically useful is the exact same proximity that gives its coastal communities almost no margin if the volcano ever lets go again. There is one more grim wrinkle. A collapse does not have to be the entire cone to be deadly. In 2018, as we'll see, it was a partial failure of one flank, a fraction of the mountain, and it still killed hundreds. So the danger is not gated behind some rare total destruction of the island. A comparatively modest slice detaching at the wrong moment into the right stretch of deep water is enough. That lowers the bar for catastrophe in a way that should focus the mind. That is the nightmare scenario. And I want to be very careful and very honest here, because this is where responsible coverage matters. That scenario is not something I am inventing to frighten you. It is not a what-if pulled from the 1800s. It is not ancient history. It happened here, at this exact volcano, within living memory. And I want to underline how ordinary the volcano can look while it is quietly setting that trap. A cone that is growing looks, from a distance, like a volcano doing what volcanoes do. Ash goes up, it comes down, the island gets a little taller. Nothing about that outward picture screams that a slope is approaching the point of failure. The instability builds inside the geometry, in the steepness of the underwater flank, in the strength or weakness of the loose material, in stresses that are invisible from the deck of a passing boat. That is the cruelty of this hazard. The very activity that is rebuilding the cone, and that looks like a manageable, watchable eruption, is the same activity that is loading the slope. The threat grows out of the normal behaviour, not out of some obvious dramatic warning sign. It happened on a December night in 2018, and it killed hundreds of people who never felt a single warning. The current eruptions, the 6 in one day, the black ash, the sustained tremor, the raised alert level, all of it draws its real weight from that one night, because that night proved the domino chain is not theoretical. So let me take you back to it, because you cannot understand the fear in this story without understanding what already happened once, when the same volcano was doing something that looked a lot like what it is doing right now. Part 5. The night. The flank fell. It was the 22nd of December, 2018. Late evening. A holiday weekend was underway, and along the coasts of the Sunda Strait, on both the Java side and the Sumatra side, people were doing exactly what you would expect people to do near a beautiful stretch of water during a holiday. They were near the water. At a beachside resort, a band was playing on an outdoor stage a few steps from the shoreline. Families were out. It was, by every ordinary measure, a normal night. Out in the strait, Anak Krakatau was erupting. It had been active for months, and to anyone watching, it looked like more of the same. There was nothing on that particular evening that screamed catastrophe. And then, during the eruption, part of the volcano's southwestern flank gave way. A section of the cone, a landslide estimated at less than 0.2 of a cubic kilometre of material, detached and slid into the sea. Here is the detail that matters most, the one that makes this event so uniquely terrifying, and I need you to really hear it. There was no giant earthquake first. There was no violent shaking that sent people running from the beach. There was no long, ominous rumble that gave anyone a head start. The kind of tsunami most of us have a mental model for, the kind from 2004 in the Indian Ocean, or from 2011 in Japan, begins with a massive undersea earthquake, and as horrifying as those were, they at least came with a signal. The ground shook, seismic networks lit up. There was in some form a warning, however short. This was different. A landslide does not produce the strong long-period seismic waves that a great earthquake does. So when the flank of Anak Krakatau slid into the sea, it did not ring the alarm bells. The seismic networks did not register the kind of signal that triggers a tsunami warning. There was no shaking on the coast for anyone to feel. There was no countdown, no message that a wave would arrive in a certain number of minutes. There was just the sea, drawing itself up in the dark and then arriving. The tsunami swept the coasts of Java and Sumatra sometime between roughly 9:30 and 10 o'clock that night. On the coastlines nearest the volcano, the run-up, The height the water reached as it came ashore climbed to as much as 13 meters in places. That is over 40 feet of water arriving without warning, in the dark, onto beaches full of people who had felt nothing at all. The band playing at that beachside resort was swept off the stage mid-performance, a moment that was, horrifically, captured on video and seen around the world. That footage is part of why 2018 lodged so deeply in the public memory. It was not an abstraction, not a number in a report. It was a stage, a crowd, music, and then, in an instant, the water taking all of it. There was no scramble beforehand, no visible panic, because there was nothing to panic about until the wave was already there. People were relaxing, celebrating, close to the shoreline on a holiday night, doing the most human and ordinary thing imaginable, and the sea arrived without preamble. If you want to understand why researchers and officials treat this volcano with such gravity, that video is the reason. It is the difference between knowing intellectually that a flank collapse can kill and having watched it happen. Consider the timeline of that night in human terms, because it is the timeline that makes it so chilling. The collapse happened during the eruption, sometime in the evening. The water arrived on the nearest coasts roughly between 9:30 and 10 o'clock at night. That is a window of, in many places, only tens of minutes between the flank failing and the wave coming ashore. And across that entire window, the people on the beaches had no information at all. There was no felt earthquake to make anyone uneasy. There was no official warning issued in time, because the event that generated the wave did not trip the systems designed to detect tsunamis. The sea simply withdrew and returned in the dark at a moment when the water's edge was crowded with people who had every reason to feel safe, and the water did not arrive at one uniform height. The physics of a landslide tsunami tends to concentrate the largest waves closest to the source, and on the small islands nearest the volcano, the run-ups were extreme, far higher than what struck the mainland coasts. On the more distant populated shorelines of Java and Sumatra, in regions like Banten and Lampung, the waves came ashore at heights reaching up to about 13 meters in the worst hit spots. 13 meters of black water, over 40 feet, moving inland across resorts and villages and roads. The landslide itself was not even enormous by the standards of what this volcano is capable of, an estimated less than 0.2 of a cubic kilometre of material. It did not take a colossal collapse. A relatively modest piece of the mountain dropped into deep water in the right place was enough, and that is perhaps the single most important lesson of that night, the one that should stay with you as we look at the current activity. We tend to assume that a catastrophe requires a catastrophe-sized cause, that only a monstrous eruption could produce a deadly wave. 2018 proved otherwise. The eruption that accompanied the collapse was not, by this volcano's historical standards, extraordinary. It was the collapse itself, the geometry of loose material sliding into deep water, that did the killing, and that collapse was a fraction of the island. So when someone looks at the current eruptions and says, well, these are not huge, the ash is only a few hundred meters, remember that huge was never the requirement. The requirement was a piece of the flank and deep water beneath it, and both of those are present today. At least 437 people were killed. Thousands were injured. Tens of thousands were displaced from their homes. It was the deadliest volcanically triggered tsunami since the 1883 eruption of Krakatoa itself, the very event that gave this volcano its name and its reputation, and there is a bitter symmetry in that. The parent volcano killed by tsunami in 1883, then the child, born from the parent's ruins, killed by tsunami again in 2018, more than a century later, on a smaller but still devastating scale. Same place, same mechanism, same sea, different generation of the same volcano. It is as if the location itself has a way of killing, and it passes that way down from parent to child. That continuity is exactly why nobody who understands the history treats the current eruptions casually. The pattern is not ancient and abstract. Its most recent chapter is only a handful of years old, and the volcano writing it is the same one throwing black ash into the sky this month. And it was caused not by a great explosion, not by an earthquake, but by a piece of an island falling into the ocean during an eruption that, from the outside, had looked routine. That is the precedent. That is why a 3-kilometre exclusion zone is not decoration, and that is why 6 eruptions in a day, black ash, and sustained tremor are not just an interesting spectacle. Because the last time this volcano was in a sustained eruptive phase and its flank was under stress, the result was 437 funerals. The aftermath reshaped how this volcano is understood and watched. Before that night, The flank collapse tsunami was a hazard scientists knew was theoretically possible and had studied in historical cases. After it, the threat was no longer theoretical here. It had a body count, it had video, it had a date. Monitoring of Anak Krakatau intensified, the exclusion zones and alert protocols took on new seriousness, and the phrase silent tsunami entered the public conversation about this place. In a sense, everyone watching the volcano today, including us, is watching it through the lens that December night ground into the glass. That is why a sequence of eruptions that might, at some anonymous volcano, be a minor regional story becomes here a story the whole world checks in on. The precedent is doing the work. It has taught us exactly what this specific mountain is capable of, and it has taught us that the warning we most want, the one that says a wave is coming, is the one this volcano is least likely to give. Now, I am not telling you the current eruption will end the same way. I will come back to that, honestly, later, because there are real reasons the risk right now is lower than it was in 2018. But to understand why anyone is worried at all, you have to understand the mechanism that made that night possible, because it is a genuinely different kind of monster than the tsunamis most of us have learned to fear. Part 6. A wave that sends no warning. Let us talk about why a landslide tsunami is such a different beast from the tsunamis you have probably heard about, because the difference is the entire reason this volcano is treated as one of the most dangerous on the planet rather than just another mountain that occasionally smokes. Most people's understanding of a tsunami is built on the two great disasters of this century. 2004, when a magnitude 9 earthquake off Sumatra sent waves across the Indian Ocean and killed well over 200,000 people, and 2011, when the Tohoku earthquake off Japan drove a wall of water over the seawalls and into Fukushima. Both were caused by megathrust earthquakes, sudden vertical movements of the seafloor over enormous areas, and both, for all their horror, came with a physical signal. The Earth moved. Seismometers around the world registered it within seconds. Warning systems, where they existed, had something to detect. It is worth pausing on the scale of those two events, because they define what the word tsunami means in most people's minds. The 2004 Indian Ocean disaster killed well over 200,000 people across a dozen countries, some of them thousands of kilometers from the earthquake, as the waves radiated out across an entire ocean basin over many hours. The 2011 Tohoku event in Japan generated waves that overtopped seawalls built specifically to stop them, drove miles inland, and triggered the meltdowns at Fukushima. Those are the archetypes, and crucially, both of them were, in the technical sense, detectable in advance of the waves reaching distant shores. The earthquakes announced themselves globally in seconds. Deep ocean buoys measured the waves passing. Warning centers issued alerts. For faraway coasts, there were hours of lead time. The system, imperfect as it was, functioned because the source was a great earthquake that the whole planet could hear. A flank collapse tsunami works on a completely different principle. There is no fault rupture. There is no sudden slip of a plate boundary. Instead, a mass of solid material, a piece of the volcano, slides into the water and physically shoves it aside. The wave is not born from the seafloor heaving. It is born from displacement, from the simple, brutal physics of dropping something enormous into a pool. Imagine the splash when a large rock is thrown into a pond, then scale that up to a chunk of a mountain falling into a strait, and you have the essence of it. And because the trigger is a landslide rather than an earthquake, it is nearly silent to our warning systems. The collapse does not generate the strong, long-period seismic waves that tsunami detection depends on. So the very technology we have built to give coastal communities those precious minutes of warning can be effectively blind to this kind of event. The wave can be on its way before anyone knows a collapse has even happened. In 2018, the distances across the Sunda Strait are short, and the nearest coasts had almost no time at all. The water arrived, in some cases, within tens of minutes of the collapse, onto shores where no one had felt a thing. Now, in the years since 2018, there has been real effort to close that gap, to build detection specifically for volcanic tsunamis, rather than only for the earthquake kind. Some approaches look at the pressure waves in the air and sea that a collapse or a big eruption generates, others at coastal water level sensors that could catch an incoming wave a few crucial minutes before it lands. And there is ongoing work on tying volcano monitoring directly into tsunami warning, so that a sudden change at the volcano can trigger a coastal alert. These are genuine improvements, but the fundamental problem does not fully go away, because with a close-in source there is only so much warning that physics will allow, no matter how good the sensors are. When the volcano is right there in the strait, the wave simply does not have far to travel. The most reliable protection remains the boring, unglamorous one, keeping people back from the danger zone in the first place, which is exactly what that expanded exclusion zone is trying to do. And Anak Krakatau in 2018 was not the first time in history that a volcano killed by collapsing rather than by exploding. There is a grim precedent from more than a century earlier, in 1888, when a volcanic island called Ritter Island, off the coast of what is now Papua New Guinea, underwent a massive sector collapse. A huge portion of the island slid into the sea, generating tsunamis that struck neighbouring coastlines and killed people who, once again, had no earthquake to warn them. Ritter Island is studied to this day precisely because it is one of the clearest historical examples of a volcano's flank failing on a large scale and drowning people through displacement alone. The 2018 Sunda Strait tsunami was, in fact, described as the deadliest volcanically induced tsunami since the 1883 eruption of Krakatoa and that Ritter Island collapse of 1888. This is a real recurring category of disaster, not a freak one-off. Volcanic islands around the world bear the scars of ancient collapses far larger than anything in recorded history, enormous horseshoe-shaped gaps carved out of their flanks, where entire mountainsides once slid into the sea. Geologists find the debris of these prehistoric collapses spread across ocean floors, and the tsunamis they would have generated dwarf anything humans have witnessed. Anak Krakatau's 2018 event was, in the grand scale of these things, a small one, and it still killed hundreds. That should reframe how you think about the current activity. We're not worried about a wildly improbable event. We're worried about a well-documented, physically ordinary process that this specific volcano has already demonstrated it can do, in living memory, to deadly effect. There is also a cruel scaling effect that makes these events so hard to prepare for. With a great earthquake tsunami, the enormous energy is released over a huge area of seafloor, and warning centres can model where the waves will go and roughly when they will arrive, because the source is well characterised within minutes. A flank collapse is fast, local, and geometrically messy. The direction the material falls determines which way the biggest waves go, and that is not something you can predict in advance. It concentrates its worst energy on whatever coastline happens to lie in the path of the slide. So even in a region that knows tsunamis well, that has drilled for them and built warning networks for them, this particular flavour can slip through, because it does not look like the thing the networks were built to catch. This is what people mean, on this channel and in the scientific community, when they talk about the silence being the danger. With most natural disasters, the threat announces itself. The sky darkens before the storm, the ground shakes before the great wave, but a volcanic flank collapse can arrive out of an ordinary evening from a volcano that has been erupting for weeks in a way that looked manageable, and the first warning many people receive is the water itself. This is also why scientists study the 2018 event so intensely, reconstructing it wave by wave with computer models and field surveys of how high and how far the water reached. The goal is not morbid curiosity. It is to understand the relationship between the size of a collapse, the depth of the water, and the height of the resulting wave, so that if instruments ever do catch a flank beginning to move, responders have some basis for predicting what would follow. The research from 2018 has become a kind of template for the whole category of volcanic landslide tsunamis, precisely because it was so well documented, so recent, and so deadly. Every lesson from that night feeds directly into how seriously the current escalation is being treated. Now hold that thought against what is happening today. Anak Krakatau is erupting repeatedly. The cone is being loaded and stressed. The tremor is sustained. Every one of those factors is a factor that, in 2018, preceded a collapse. That does not mean a collapse is imminent. It means the ingredients that make this volcano uniquely lethal are, once again, present. And that is really the whole reason this story deserves attention rather than a shrug. If Anak Krakatau were a landlocked mountain, 6 eruptions in a morning would be a regional aviation and ashfall concern, serious but bounded. Because it is this volcano, in this strait, with this history, those same 6 eruptions carry a shadow the landlocked version never could. The shadow of a wave with no warning. The eruptions themselves may never lead there. But the fact that they could, at this specific place, is what transforms a routine volcanic sequence into something worth watching with genuine care. And the danger is amplified enormously by one more thing, something about where this volcano sits. Because Anak Krakatau is not erupting in the middle of an empty ocean, it is erupting in the middle of one of the busiest, most populated stretches of water in the entire world. Part 7. The busiest water in the world. Look at a map of where this volcano actually sits, and the danger stops being abstract. Anak Krakatau rises out of the Sunda Strait, the channel of water that separates two of Indonesia's largest islands. To the west is Sumatra, to the east is Java, and to the north and south are busy, busy waters. This is not a remote outpost. The Sunda Strait is a working seaway. It is lined with fishing areas that thousands of people depend on for their living. It is dotted with coastal towns and villages, communities that sit right at the water's edge on both sides of the strait. And it is a shipping route, a corridor that vessels move through constantly. So when this volcano throws ash into the sky, or, far worse, sheds part of itself into the sea, it is doing so surrounded by people. Fishermen out on the water, families in coastal towns, ships passing through. This is the opposite of a volcano erupting when no one will be hurt. To grasp the exposure, think about who and what is actually within reach of this volcano. Java, to the east, is one of the most densely populated islands on the entire planet, home to well over 100 million people, and its western coast faces directly into the Sunda Strait. Sumatra, to the west, carries its own large coastal population on the far side of the same water. Between them, the strait itself is alive with activity. Small fishing boats working the waters every day, ferries, cargo vessels, and the constant traffic of a channel that connects the Java Sea to the Indian Ocean. The coastlines on both sides are lined with towns, resorts, and villages that sit low and close to the shore, exactly the kind of settlement pattern that a landslide tsunami exploits. When the 2018 wave came, it came onto shores like these, full of people, at the worst possible hour. So this is the uncomfortable arithmetic that hangs over every eruption. It is not just that the volcano is capable of producing a wave with no warning. It is that if it ever does, that wave will not travel across empty ocean before dissipating. It will have populated coastline within minutes in almost every direction. A volcano with this failure mode in the middle of a truly empty sea would be a scientific curiosity. This same volcano in this particular strait, with these particular neighbours, is something else entirely. And the strait is not just a place where people happen to live. It is a strategically and economically important passage, one of the routes that connects the Indian Ocean to the interior seas of the Indonesian archipelago. Vessels of all sizes move through it, and the waters around the volcano are worked hard by local fishermen whose entire economy is built on being out there. So the exposure is not only the coastal population sitting still on the shore, it is also a moving population of boats and ships passing through the very zone where the volcano is most dangerous. A wave born at the island, or even a large enough eruption throwing material and generating local disturbances, threatens not just the fixed communities on Java and Sumatra, but everything transiting the channel at that moment. Few volcanoes on Earth combine an unstable, active edifice with this density of people and traffic packed so tightly around it. The hazard and the exposure are stacked directly on top of one another, and that is precisely why the exclusion zone matters and why it was expanded. During the earlier phase of this reactivation in late June, when the volcano was at a lower alert level, the exclusion zone was 2 kilometers. Now, with the alert raised to level 3, it has been pushed out to 3 kilometers. That expansion is a direct statement. The authorities are drawing the danger circle wider because they judge the danger to be greater. Boats are being kept back, fishermen are being warned off. Tourists, who in calmer times come specifically to see this famous volcano up close, are being told to stay away. Every one of those restrictions carries an economic cost to real people, which is worth remembering the next time someone suggests the authorities are downplaying the threat. They are not downplaying it. They are actively shrinking the crowd. There is a human tension baked into this that is worth naming. For the fishing communities of the strait, the water is not a hazard map, it is a livelihood. Being told to stay 3 kilometers back from the crater means lost fishing days and lost income for people who often do not have much cushion. For the tourism operators who, in calmer times, run boats out to let visitors witness one of the most famous volcanoes on Earth up close, an elevated alert level and an expanded exclusion zone mean cancelled trips and empty seasons. These restrictions cost real people real money, and that is exactly why they carry weight as evidence. Nobody imposes those costs lightly. When an agency accepts the economic pain of pushing everyone back and keeping them back, it is telling you, in the most concrete way available, that it judges the threat to be worth that price. The exclusion zone is not a sign that the danger is being exaggerated. It is a sign that it is being taken seriously enough to hurt. Why does a volcano even exist in this exact spot, threading the needle between two enormous islands? The answer lies deep beneath the strait, in the machinery that has been building and destroying this place for far longer than there have been people to watch. The Sunda Strait sits on top of one of the great tectonic engines of the planet, and that engine is the reason Krakatoa has erupted before, will erupt again, and has the raw power to reshape coastlines. But before we go down to the plate boundary, we have to go back in time to the event that made the name Krakatoa mean something in the first place. Because the reason the whole world tenses up when this volcano stirs is not really about 2018. It is about a single morning in 1883, when this same place produced what may have been the loudest sound a human being has ever heard. Part 8. The loudest sound in history. In 1883, the volcanic island of Krakatoa sat in the Sunda Strait, in what was then part of the Dutch East Indies, the territory we now call Indonesia. It had begun erupting, and the eruption did not resolve quickly. It built and built over a period of months. And then, on the 27th of August, it delivered its most significant eruption, an event so violent that it has become a permanent benchmark for what a volcano is capable of doing to a planet. One thing worth holding on to is that 1883 was not a single instantaneous event out of a clear sky. The eruption built over a period of months. There were earlier phases of activity through the summer, ashen explosions that were dramatic enough to draw sightseers and to worry the people living nearby before the climax arrived. That slow build is part of why the parent eruption is such a useful and sobering reference point, because it is a reminder that these great events can have long, escalating preludes, phases of increasing activity that only in hindsight are recognized as the approach to something enormous. I am not saying the current activity is such a prelude. I am saying that a volcano with a history of building toward catastrophe over months is a volcano whose escalating phases deserve to be watched rather than dismissed. The climax on the 27th of August came as a series of explosions, each more violent than the last, culminating in the third and largest blast. And the scale of it broke the instruments of the age and the imaginations of the people who witnessed it. Ships at sea, dozens and even hundreds of kilometers away, recorded the concussion. Sailors reported the sound as being like distant heavy gunfire, and in some cases the pressure of the blast was strong enough to be physically felt aboard vessels far from the island. This was a sound that did not just travel, it pressed against the world. That eruption destroyed over 70% of the island and the surrounding archipelago. The island did not just erupt, it came apart. The northern two-thirds of it collapsed into the emptied magma chamber below, into the caldera. That is the mechanism of caldera formation, and it is worth understanding because it is a different kind of collapse than the flank failure we have been discussing. When a volcano erupts an enormous volume of magma very quickly, it empties the chamber beneath it. Suddenly there is a vast void where there had been supporting magma, and the roof of that void, the mountain itself, has nothing left to stand on. So it founders, dropping down into the space its own eruption created, leaving behind a great bowl-shaped depression, the caldera. In 1883, that founding of the island into the sea was itself part of what drove the killer tsunamis, as huge volumes of rock and water rearranged themselves in an instant. The caldera left behind is the submarine bowl that Anak Krakatau, the child, would eventually rise from decades later. On the scale scientists use to rank explosive eruptions, the Volcanic Explosivity Index, this event is estimated at a 6. That is in the category they describe with the almost comically understated word colossal. It stands as one of the most destructive volcanic events ever recorded in human history, a benchmark against which later eruptions are still measured. When scientists want to convey the raw scale of what a volcano can do, 1883 Krakatoa is one of the first names they reach for, precisely because so much of its devastation was documented and measured even by the standards of the day. Now let me try to give you a sense of the raw power involved, because the numbers are almost difficult to believe. The third and largest explosion of that day is regarded as producing one of the loudest sounds in recorded history. That sound was heard about 3,110 kilometres away. That is nearly 2,000 miles in Perth, Western Australia. People there heard it and in many cases had no idea what it was. It was also heard near Rodriguez Island, out by Mauritius, about 4,800 kilometres away. That is roughly 3,000 miles. Sit with that for a moment. A volcano in Indonesia made a sound that people heard 3,000 miles away, across open ocean, with no idea of the source. To put a human face on it, there are accounts of people at that enormous distance who assumed they were hearing the guns of a ship in distress or distant cannon fire and organised responses to a battle or an emergency that did not exist. The sound was so far outside the range of anything they had a reference for that they reached for the loudest human-made thing they knew, warfare, and even that fell short. What they were actually hearing was a single mountain tearing itself apart on the far side of an ocean. There is genuinely no other documented sound in human history that travelled so far and was heard so widely. It sits alone at the top of that list, and it came from this exact stretch of water we are watching right now. And the sound did not simply travel and fade. The atmospheric pressure wave from the explosion is documented to have travelled around the entire globe. Not once. Barographs, the instruments that measure air pressure, recorded the pulse passing by again and again as it circled the planet at least 3 times and more. The Earth's atmosphere rang like a struck bell, and the ringing went around the world for days. This was measured, not merely felt. Weather stations across Europe and North America, thousands of kilometres from any volcano, recorded sudden little jumps in atmospheric pressure at intervals that lined up precisely with a wave travelling outward from Indonesia, passing, circling the globe, and coming back around again. Scientists at the time could track the pulse making its laps around the planet on their instrument charts. It is one of the earliest cases in which a local geological event was documented in hard data to have physically disturbed the entire atmosphere of the Earth. A single volcano, on a single morning, made the whole sky flinch in a way that pens on paper thousands of miles away faithfully recorded. But the sound, as staggering as it is, was not the killer. The killer was the water. The collapse and the explosions displaced the sea on an enormous scale, and the tsunamis that followed did the vast majority of the dying. At least 36,000 people were lost, the great majority of them to those waves. The largest local tsunami reached on the order of 40 metres in height, well over 100 feet, sweeping away coastal towns on both sides of the strait. Some people compare the explosive force of the whole event to a bomb on the order of 200 megatons, and notice the through line here, the thing that connects 1883 to 2018 to right now. In every case, at this volcano, the greatest loss of life came from the sea, from displaced water, from a wave. It was true in 1883, when the tsunamis, not the explosion or the ashfall, killed the tens of thousands. It was true in 2018, when a landslide wave, not the eruption itself, killed the hundreds. This is the signature of Krakatoa across a century and a half. Whatever the scale, whatever the trigger, the thing that ends up killing people here is water thrown out of its place. That is not a coincidence. It is the direct consequence of a volcano that lives in the middle of a strait, surrounded by deep water and low populated coasts. The sea is always right there, waiting to be displaced. And that is precisely why, when this volcano stirs, the experienced response is not to stare at the height of the ash, but to think immediately about the water, because the water is where the history of death at this place actually lives. That is the pedigree of the place we are watching today. And the strangest, most haunting part of the 1883 story is not what happened at ground level at all. It is what the eruption did to the sky over the entire planet for months afterward, and it gave the world a phrase that sounds like poetry, but was born from catastrophe. Part 9. The Year of Blue Moons. When Krakatoa exploded in 1883, it did not just move water and shatter eardrums across an ocean. It reached into the stratosphere and changed the colour of the sky for the whole world. People at the time called it, among other things, a year of blue moons. And that was not a metaphor. Here is what happened. The eruption injected an immense quantity of material high into the atmosphere, far above where weather happens, up into the stratosphere. Sulfur dioxide gas and fine volcanic ash and aerosol particles spread out and formed a veil around the planet. And that veil did something strange and beautiful to sunlight. It filtered the colours of the light reaching the ground. Sunsets around the world turned lurid shades of red and orange and green, and the moon, seen through that high haze of just the right-sized particles, could appear to shift colour, taking on a blue or greenish cast at night, hence the year of blue moons. The effect was so pronounced and so widespread that it was noticed and recorded across continents by people who had no way of knowing its cause. In some places, the fiery evening skies were vivid enough that observers mistook them for distant fires and summoned help. That is the reach of a single large eruption. It does not just alter the country it happens in, it repaints the sky for the entire planet, night after night, for months, until the last of the fine ash and acid droplets finally drift back down to Earth. The atmosphere is a shared thing, and when a volcano injects itself into the high stratosphere, it is writing on a canvas that everyone on Earth is looking at. But the veil did more than paint pretty skies. It acted as a sunshade for the entire Earth. By reflecting a portion of incoming sunlight back into space before it could warm the surface, that stratospheric layer cooled the planet. Global average temperatures dropped by roughly 0.6 of a degree Celsius in the period that followed. That may not sound like much when you say it quickly, but a global average temperature shift of over half a degree, imposed on the whole planet by a single volcano in a single day, is a genuinely enormous thing. One mountain, coming apart in Indonesia, turned down the thermostat for the whole world. The mechanism behind that global cooling is worth understanding, because it is the same process that operates after every truly large eruption, and it hinges on one particular ingredient: sulfur. When a volcano injects sulfur dioxide gas high into the stratosphere, that gas reacts with water vapour to form tiny droplets of sulfuric acid, an aerosol haze of particles so fine they can stay suspended for months or even years. Down in the lower atmosphere, rain would wash such particles out in days. But up in the dry, stable stratosphere above the weather, there is nothing to rinse them away. They spread into a planet-wide veil, and that veil is highly reflective. It bounces a fraction of incoming sunlight straight back into space before it can ever reach the ground and warm it. More sunlight reflected means less heat delivered to the surface, and the whole planet cools until the aerosols finally settle out. It is, in effect, a natural and temporary version of the exact thing some scientists now nervously discuss as deliberate climate intervention, an accidental global sunshade thrown up by a single mountain. And here is the sobering context. As catastrophic as Krakatoa in 1883 was, it is not even the deadliest eruption of the modern era. That grim distinction belongs to another Indonesian volcano, Tambora, which erupted in 1815 and ended the lives of something on the order of 60,000 people or more. Tambora's climate effects were so severe that the following year, 1816, became known across the northern hemisphere as the year without a summer, with crop failures and frosts in the middle of what should have been the growing season. In New England, there was snow in June and killing frosts in July and August that destroyed harvests. In Europe, cold and relentless rain ruined crops and drove food prices to famine levels, contributing to some of the worst hunger the continent had seen in a century. The gloomy, sunless weather of that summer even seeped into art and literature. It was during that dismal, storm-bound season by a lake in Switzerland that a young writer, kept indoors by the endless rain, conceived one of the most famous horror stories ever written. A single Indonesian volcano, in other words, reached across the entire globe and touched harvests, economies, and even the imagination of people who had no idea why the sun had gone dim. That is the kind of planetary leverage this one stretch of the Sunda Arc has demonstrated, not once, but repeatedly. Indonesia, sitting where it sits on the planet's tectonic machinery, has produced not one but two of the most consequential eruptions in all of recorded history. That is not a coincidence, and it is worth understanding why. The same subduction system that we will look at more closely in a moment, the great collision of plates that runs the length of the archipelago, is one of the most productive magma factories on Earth. It builds volcanoes with the potential to erupt enormous volumes of material, and it packs them into a region that has been densely populated for a very long time. So Indonesia is not simply unlucky. It is geologically predisposed to produce the largest eruptions, and demographically arranged so that when those eruptions come, enormous numbers of people are in reach. Krakatoa and Tambora are the two most famous names on that grim list, but they sit within a much longer catalogue of Indonesian volcanic disasters. The current activity at Anak Krakatau is a small entry in that catalogue, but it is written by the same hand. Now, I want to bring you back from 1883 to today, and I want to do it carefully, because it would be dishonest to let the story of that colossal eruption sit next to the current activity without drawing the line clearly. What is happening at Anak Krakatau right now is nowhere near 1883. The ash columns we are seeing are measured in hundreds of metres, not tens of kilometres. This is not a colossal caldera forming eruption in progress. I am not telling you that a 200 megaton, globe-cooling, sky-bluing event is unfolding this week. It is not. But here is why the 1883 story is not just a history lesson. The Anak Krakatau we are watching today, the child, is growing inside the very caldera that the 1883 collapse created. It rose from the submarine wreckage of its parent, first emerging above the waves in the late 1920s. Think about what that means. After 1883, where the island had been, there was mostly water, a great submerged bowl the caldera left behind when the old volcano collapsed into its emptied chamber. But the tectonic engine did not switch off. Magma kept rising through the same weak point. And in the late 1920s, roughly 4 decades after the parent destroyed itself, a new cone built up from the floor of that submarine caldera and broke the surface of the sea. The people of the region watched a brand new island being born out of the water, and they named it the Child. Since then it has grown and collapsed and grown again in cycles, because that is what a young volcano fed by an active subduction zone does. The Anak Krakatau erupting today is only about a century old as a landform, a geologically newborn mountain, and newborn mountains are, almost by definition, poorly built and unstable. It is, quite literally, built on the grave of the volcano that made the loudest sound in history, and it sits on the same tectonic engine, the same source of magma, the same fault in the planet that fed the parent. So to understand not just the child's past but its future, we finally have to go down beneath the strait to the machine that makes all of this inevitable. Part 10. The engine beneath the strait. Every volcano is the visible top of an invisible process, and the process beneath the Sunda Strait is one of the most powerful on the planet. South of Java and south of Sumatra, out under the Indian Ocean, one enormous slab of the Earth's outer shell is being forced beneath another. The Indo-Australian plate is diving down under the Sunda plate, the block that carries this part of Indonesia, along a boundary called the Sunda subduction zone, marked at the surface by the deep Sunda Trench. When one plate is driven down beneath another like this, extraordinary things happen at depth. The descending slab carries water and sediment down with it, and as it sinks into the hot interior, that water lowers the melting point of the surrounding rock. Magma is generated, and because magma is less dense than the solid rock around it, it rises. Over millions of years, that rising magma builds a chain of volcanoes running parallel to the trench, a volcanic arc. There is a beautiful and slightly terrifying counterintuitive fact buried in that process. You would think that shoving a cold slab of ocean floor down into the hot interior of the Earth would cool things off, not start fires. But it is the water riding down on that slab that does the work. Rock that is bone dry can stay solid at temperatures that would melt the same rock if water were present, because water lowers the melting point dramatically. So as the descending Indo-Australian plate reaches a depth of roughly 100 kilometres, it starts to sweat out the water locked in its minerals. That water rises into the wedge of hot rock above the slab, and that rock, suddenly wet, begins to melt. The melt is buoyant, less dense than the solid rock around it, so it rises, collecting into chambers, feeding upward, until it finds a path to the surface. The volcano is the chimney at the top of that column. Krakatoa is simply where, in this particular stretch of the Sunda arc, the chimney happens to reach the sky. And the convergence never stops. The plates move at a pace of centimetres per year, about as fast as your fingernails grow, which sounds trivial until you multiply it by millions of years and the entire width of an ocean. That relentless, imperceptible creep is the ultimate power source behind everything in this story, every eruption, every earthquake, every collapse. The Sunda arc runs the length of Indonesia, and it is studded with some of the most active and dangerous volcanoes in the world. Krakatoa is one link in that chain. This is the same tectonic engine that produced Tambora. the same broad system that makes Indonesia one of the most volcanically active nations on Earth, all part of the great circle of subduction zones and volcanic arcs we call the Pacific Ring of Fire. So the existence of Anak Krakatau is not an accident, and neither is its persistence. As long as that plate keeps diving beneath the strait, and it will for a very long time, magma will keep being generated, and it will keep finding its way up through the weak point that Krakatoa has occupied for as long as we have records. And Indonesia sits at the sharp end of this process like almost nowhere else on Earth. It is home to more active volcanoes than any other country, well over 100 of them, strung along the arcs where the Indo-Australian plate and other slabs dive beneath the region. That is why the nation maintains a dedicated volcanology agency, running constant surveillance on dozens of restless mountains at once. Krakatoa is one entry on a very long and very active list, but it holds a special place on that list because of where it sits. Most of Indonesia's dangerous volcanoes are on land, threatening the communities around their base with ash, lava and pyroclastic flows. Krakatoa is out in the water, in a narrow strait, between two of the most populous islands on the planet, which gives it that extra, rarer seaborne failure mode. It is not the biggest volcano in the arc, nor necessarily the most explosive on any given day. But the combination of an unstable island edifice, deep surrounding water, and dense population on every shore is what earns it a reputation out of proportion to its size. Danger, in volcanology, is never just about how big or how violent a volcano is in isolation. It is about the intersection of the hazard with the people in its reach. A colossal eruption in an empty wilderness harms no one. A modest collapse in a crowded strait can kill hundreds. Anak Krakatau is dangerous not because it is the mightiest mountain in Indonesia, but because its particular failure mode and its particular address line up so perfectly and so lethally over so many people. The volcano is not an isolated event. It is a permanent feature of a permanent process. The child will keep being fed. This is the same great system, the Pacific Ring of Fire, that connects Indonesia's volcanoes to the earthquakes of Japan, the eruptions of the Philippines, the volcanoes of the Andes, and the seismic threats of the west coast of North America. It is not a single fault or a single feature. It is the horseshoe-shaped belt of subduction zones and volcanic arcs that rings the Pacific and its margins, the most geologically violent zone on the planet, and it is violent for exactly the reason we have been describing, because it is where the great oceanic plates dive down and remake the crust. Anak Krakatau is one small, fierce expression of that global machine. When you watch this volcano, you're watching one visible spark thrown off by a process that spans the entire Pacific Rim and never, ever stops. And that is the connection back to everything we have been watching. The tremor, the 6 eruptions, the black ash. They are all the surface expression of this deep engine pushing fresh magma up into a young, unstable cone. The plate boundary is why there is a volcano here at all, why it rebuilds itself after every collapse, and why the loose new material keeps piling up over deep water in exactly the configuration that led to disaster in 2018. And it reframes the whole question we should be asking. We tend to talk about whether the volcano will erupt, as if eruption were the exception and calm the rule. But for a volcano sitting on top of an active subduction zone, eruption is the rule. The magma supply is not going to run out. The plate is not going to stop diving. So the honest long-term picture is not whether Anak Krakatau will be dangerous again, but when and in what form, and whether we will be watching closely enough when it is. The current escalation is one episode in a story that has no ending as long as the engine runs. That is not a reason for despair. It is a reason for the kind of steady, permanent vigilance that the monitoring agencies have built their entire existence around. You do not get to solve a volcano. You only get to watch it well. Understanding the engine does not calm the situation. It explains why the situation keeps coming back. Part 11. What the Skeptics Say. Whenever a volcano like this starts making headlines, a second story always rises alongside the real one. And I think it is worth meeting that second story head-on, honestly, because dismissing people's questions never actually answers them. So let us walk through the alternative explanations that circulate online whenever Anak Krakatau stirs, and let us take them seriously enough to actually examine them. The first and most common is the idea that the eruption is somehow engineered, that it is being caused deliberately by human technology, whether that is described as weather manipulation, high-frequency antenna arrays, or some form of geoengineering. I understand the instinct. When something powerful and frightening happens, It can feel more bearable to imagine a hand on a lever than to accept that the planet simply does this on its own. But the numbers make this one impossible. The energy released by even a modest volcanic eruption dwarfs anything human technology can produce by many orders of magnitude. Let me put a little more weight on that energy argument, because it is the thing that actually settles the question rather than just asserting it. The energy stored in and released by a volcanic system is measured in scales that make our largest machines look like toys. The heat and mechanical energy involved in melting rock, driving it up through kilometers of crust, and blasting it out of a crater represents an output that our entire civilization's power generation could not match, let alone a single facility with antennas. When people point to some transmitter array and imagine it is nudging magma, they are imagining a garden hose steering a hurricane. The mismatch is not a matter of 10% or 100%. It is a matter of many, many orders of magnitude. There is simply no known physical pathway by which the modest energy of human broadcast technology couples into the immense energy budget of a subduction zone volcano. We cannot start a volcano, and more to the point, we do not need to invent a cause, because we already have one. It is the plate diving beneath the strait generating magma exactly as it has for millions of years. The mundane explanation is also the completely sufficient one. The second claim is that authorities are secretly hiding a coming mega eruption, concealing evidence that another 1883 is imminent to prevent panic. But look at the actual behaviour. The response has been the opposite of concealment. They raised the alert level publicly. They expanded the exclusion zone from 2 kilometres to 3 publicly at a real economic cost to fishermen and tourism operators. Those are loud, visible, restrictive actions. A cover-up does not warn people away and shrink the crowd. A cover-up keeps the beaches open, and there is a hard physical ceiling on the hidden mega-eruption fear as well, one rooted in the scale that separates today's activity from 1883. Volcanologists rank explosive eruptions on the Volcanic Explosivity Index, a scale that runs from 0 up to 8, and it works a bit like the scale for earthquakes, in that each step up represents a roughly tenfold jump in the volume of material erupted. 1883 was a 6, described as colossal. The current activity at Anak Krakatau, with its ash columns measured in hundreds of meters rather than tens of kilometers, is many, many steps down that ladder. You cannot secretly hide the approach to a 6. An eruption of that magnitude requires an enormous magma body and produces unmistakable, escalating precursors over an extended period, exactly the kind of signals that are broadcast on public monitoring feeds. The instruments that are openly reporting Level 3 activity would be screaming something entirely different if a caldera-forming event were loading up. The mundane truth is that the honest, moderate hazard, a Level 3 volcano with a dangerous but specific collapse risk, is fully consistent with all the data, and there is no room in that data for a concealed apocalypse. What we are seeing is disclosure, not suppression. A third idea holds that solar activity, or the alignment of planets, is triggering the eruption. This one has a certain romance to it, the notion that the cosmos is reaching down to squeeze the Earth. But there is no established physical mechanism by which solar cycles or planetary positions deliver the energy needed to initiate an eruption at a specific volcano on a specific day, and you can test that claim against the pattern of eruptions themselves. If the sun or the planets were pulling the trigger, you would expect eruptions around the world to cluster in time with solar storms or particular alignments. They do not. Volcanoes on the same day, under the same sky, sit quiet or erupt according to their own local plumbing, not according to what the cosmos is doing. Anak Krakatau's 6 pulses on the 8th of July were governed by the pressure in its own shallow system, by gas and magma finding a path out through a specific cone on a specific island above a specific slab of descending crust. The timing was set underground, not overhead. The driver here is local and it is deep. It is the subduction zone, not the sky. And there is a fourth, more cynical version of skepticism worth addressing, the suspicion that the alert level is being kept artificially low to protect the tourist season, that money is quietly outranking safety. But again, check it against what actually happened. The level was raised to 3, the zone was widened, access was restricted. If commercial interests were secretly running the show, none of that would have happened. And this suspicion is worth taking seriously precisely because there are real cases, at other hazards in other places, where economic pressure has genuinely influenced how aggressively officials warned people. It is not a crazy thing to wonder about. The way to handle it is not to assume the worst or to assume the best, but to look at what actually happened here. And what happened here is the opposite of suppression for profit. The alert went up, not down. The exclusion zone widened, not shrank. Tourist boats were pushed back, at real cost to the operators who run them. If someone were quietly protecting the tourist trade, every one of those decisions would have gone the other way. The honest skeptic's move here is a good one, question the official line, but then follow it all the way through to the evidence, and the evidence shows an agency tightening restrictions, not loosening them. I think there is something worth respecting in the impulse behind all four of these theories, even as the evidence knocks them down. People reach for engineered causes and hidden agendas because the alternative, that the Earth simply does this, on its own schedule, indifferent to us, is genuinely unsettling. A secret weapon is, in a strange way, more comforting than a subduction zone, because a weapon implies a controller, and a controller could in principle be stopped. A cover-up implies someone knows exactly what will happen and when. Both of those are less frightening than the truth, which is that the volcano answers to physics, not to anyone's plan, and that even our best instruments cannot fully predict its most dangerous move. So I do not dismiss the questions. I just follow them all the way to the data, and the data keeps pointing at the same undramatic, sufficient answer. The real danger at this volcano is smaller than the myths, but it is far more specific. It is not a secret weapon or a hidden apocalypse. It is the island itself. Part 12. Lower risk is not no risk. I promised you honesty, so here it is, the part where I tell you why you should not spend tonight in a panic and why you also should not look away. There is a genuine science-based reason to believe the risk of a catastrophic flank collapse right now is lower than it was in 2018, and it comes down to the shape of the volcano itself. When the flank failed in 2018, Anak Krakatau lost a huge part of its height. The collapse and the eruptions that followed carved the cone down dramatically. The tall, steep edifice that had loomed over the strait was suddenly a fraction of its former self, and a lower, smaller cone simply has less mass perched over the water to shed in a single catastrophic slide. The specific geometry that made the 2018 collapse so deadly, a large, tall, steep flank, is not fully rebuilt. The volcano has not yet stacked itself back up to that dangerous height. So the odds of an identical, massive southwestern flank collapse happening this week are lower than they were on that December night. Think of it like a wave that has already broken. Immediately after 2018, the volcano had spent its dangerous shape. There simply was not a towering flank left to fail in the same way, because that flank was now on the seafloor. Rebuilding it into a comparable threat is not a matter of days or weeks. It is a matter of the slow accumulation of eruption after eruption over years. So when you ask, is tonight another 2018 waiting to happen, the geometry answers, not in that exact form, not yet. The volcano is earlier in the cycle. That is real, and it is worth holding on to when the headlines get loud. There is a useful way to think about this. The 2018 collapse did not just kill hundreds of people. It also, in a brutal sense, spent the volcano's ammunition. The large, tall flank that failed is gone. To reload that specific weapon, the volcano has to rebuild the cone back up to a comparable height and steepness, and that takes time, many eruptions, a lot of stacked material. In the years since 2018, it has been doing exactly that, slowly reconstructing itself, but it is not there yet. So in the narrow question of an identical catastrophic collapse of that same scale, tonight, the honest read is that we are earlier in the reloading cycle than the volcano was in 2018. That is genuine grounds for not panicking. That is the reassuring half of the truth, and it is real. Now here is the other half, and it is just as real. Lower risk does not mean no risk. The mountain is still erupting. It is erupting from an island, in a narrow strait, over deep water. It is still producing sustained volcanic tremor. It is still showing those hybrid and low-frequency signals that tell us gas and magma are moving under pressure. And critically, the cone is rebuilding right now out of exactly the kind of fresh, loose, poorly consolidated material that made the 2018 flank unstable in the first place. Every eruption adds another layer to a pile that has to sit on a steep underwater slope. The process that leads to instability is not paused. It is actively running. And there is a specific reason fresh material is more dangerous than old. Newly deposited volcanic rock and ash has not had time to settle, compact or bind together into anything solid. It is loose, often steep, sometimes waterlogged, and it sits at what engineers would call a marginal angle, close to the point at which gravity overcomes whatever is holding it in place. Over many years, such material can consolidate and stabilize. But a volcano in an active building phase is not giving its slopes that time. It is stacking new, weak material on top of new, weak material faster than any of it can firm up. So the very productivity of this eruptive sequence, the thing that makes it look impressive, is also quietly assembling exactly the kind of unstable slope that fails. That is the uncomfortable duality at the center of this whole story. The activity that we watch as a spectacle is the same activity that builds the hazard, and there is a subtlety here that is easy to miss. It is entirely possible for the collapse risk to be lower than 2018 in absolute terms, while still trending in the wrong direction. Every eruption in this sequence adds material to the cone. Every pulse builds the flank a little higher and a little steeper. So the volcano is, in a slow and grinding way, working back toward the configuration that failed once before. It is not there today. But a sustained eruptive phase like this one is precisely how it would get there, layer by layer, over months and years. That is why volcanologists do not treat a lower current risk as a reason to look away. They treat it as a clock that is running, and the current activity is winding it. The escalation we are watching is not just a snapshot of danger, it is potentially part of the process that rebuilds the danger. So the honest position, the one the scientists actually hold, is not that everything is fine, and it is not that catastrophe is imminent. It is that this volcano has a specific, demonstrated, uniquely dangerous failure mode, that the conditions which can lead to that failure are present again, and that the probability, while lower than in 2018, is not zero and deserves close, continuous attention. That is why the alert sits at level 3, not at 1, where it would be if this were nothing, not at 4, the highest level, which the volcano has not earned. And I want to be honest about the emotional discipline this requires, because it cuts against how our minds like to work. We are wired to want a clean verdict. Tell me it is safe, or tell me to run. This situation offers neither. It offers a probability, elevated but not certain, of a specific catastrophe, hanging over an active volcano that may keep erupting for weeks and then quiet down, or may keep building towards something worse. Living with that kind of uncertainty, watching closely without either panicking or dismissing, is genuinely hard. But it is the only rational response to a hazard that is real, serious, and not precisely predictable. The scientists have found a way to hold that posture professionally, and it is expressed in a single number on a 4-point scale, at 3, a serious, elevated, watch closely level. And the fact that it has stayed at 3 through this sequence, rather than being relaxed back to 2, is itself information. The people making that call have watched the 6 eruptions, read the tremor, tracked the ash on satellite through the 9th and 10th of July, and concluded that the conditions justifying level 3 have persisted. They have not seen enough to justify level 4, but they have also not seen the volcano calm down enough to step back to 2. It is holding at that in between, elevated posture precisely because the volcano itself is holding at an elevated, unsettled state. The alert level is not lagging behind reality, it is tracking it. The uncomfortable part is that all of that careful monitoring is best at reading the eruptive story, the part of the danger that announces itself, and weakest at the one scenario that gives no announcement. And that word, watch, is the crux of the whole thing. Because everything I have described, the tremor, the ash, the collapse risk, comes down to one uncomfortable question. Can we actually see the thing we're most afraid of coming? Do the instruments that are so good at hearing the volcano breathe give us any real ability to catch the one event that gives no warning? Part 13. What the instruments can and cannot see. Here is the paradox at the centre of this entire story. We can hear this volcano extraordinarily well, and yet the specific catastrophe we fear most is the one thing our ears are worst at catching. Think about everything the monitoring network detects. It counts individual eruptions and times them to the second. It measures the amplitude of each blast down to fractions of a millimetre. It distinguishes hybrid events from low-frequency events from harmonic tremor. It tracks continuous tremor through the quiet hours of the night. Satellites overhead watch the ash spread across the strait and measure how high it climbs, up to flight level 050 and back down. We have, in many ways, a remarkably detailed picture of what this volcano is doing from moment to moment. The eruptive activity is not sneaking up on anyone. The escalation to level 3 was made on the strength of exactly this data. But a flank collapse is a different kind of event, and it exposes the edge of what all that instrumentation can do. As we saw with 2018, a landslide does not announce itself with the strong seismic signature of a great earthquake. It can happen fast, and it can happen without the kind of clear precursor that would let anyone sound an alarm in time. So the scientists are, in a sense, watching for the shadow of the thing rather than the thing itself. They cannot yet see directly inside the island to know precisely how stable each flank is. Instead, they watch the indirect signs, the indicators that the system is heading toward the dangerous state. It helps to know the ladder they are climbing, because the alert level is not a vague mood, it is a defined 4-rung scale. Level 1 is normal, the baseline, the volcano at rest. Level 2 is Waspada, which translates roughly to be on guard, the level Anak Krakatau sat at during its late June reactivation, meaning activity is above background and worth monitoring. Level 3 is Siaga, which means stand by or be ready, and it is where the volcano sits now, signalling that eruptive activity has meaningfully increased and that hazards around the crater have grown. And Level 4 is ours, the highest, meaning a significant eruption is underway or imminent, and the widest protective measures are warranted. Moving from 2 to 3, as happened on the 2nd of July, is not a small bureaucratic tick. It is a formal judgment by the people with the most data that this volcano has entered a more dangerous phase. What are those signs, the ones on the watch list? Rising tremor amplitude, a sustained increase in the intensity of that continuous hum, a shift toward more and denser black ash, signalling stronger explosive activity, growing ash columns, climbing higher over time, visible incandescence, a glow at the crater at night that indicates fresh, hot magma very close to the surface. Each of those signs is a different sense being brought to bear on the same patient. Incandescence is the volcano's temperature taken by eye and by thermal camera, a glow that says hot magma is now within reach of the surface, rather than buried deep. Growing ash columns are its breathing rate. Rising tremor amplitude is its pulse. The shift toward blacker, denser ash is the character of that breathing, whether it is a gentle exhale of steam or a violent cough of fresh rock. Individually, any one of these can flicker up and down without meaning much. What the monitoring teams are really looking for is agreement, several of these indicators climbing together and staying up, the way the ash colour and the seismic amplitude march together on the 8th of July. When independent measures line up and point the same way, that is when confidence in a trend becomes high enough to act on, and, most directly relevant to the collapse fear, any measurable ground deformation, any swelling or slippage of the cone that would suggest a flank is beginning to move. And ground deformation, in particular, is the one they would most want to catch, because it is the closest thing to a direct read on the collapse threat. There are tools that can measure it. Satellite radar can compare the shape of the island between passes and detect swelling or subsidence of the surface down to centimetres. Instruments on the ground, where they can be safely placed, can register tilt, the subtle leaning that happens when magma inflates a flank from within. If a section of the cone began to bulge outward, that would be the signal that pressure was pushing a flank toward failure, and it would be a reason to clear the water urgently. The hard truth is that on a small, violently active, hard-to-access island, keeping such instruments running right where you would need them most is genuinely difficult, and a fast collapse might still outrun the warning. But this is the frontier they are watching, the difference between seeing the smoke and seeing the mountain move. These are the things that would drive a decision to push the alert from level 3 up to level 4, the highest level, the one that means the most serious phase of all. And this is where the current escalation earns its attention. Because when you line the July events up in order, you see a sequence, not a coincidence. First the alert level was raised, on the 2nd of July. Then the eruptions continued. Then, on the 8th, came the cluster, 6 in under 10 hours, with amplitudes climbing and the ash darkening through the morning. Then ash kept appearing on satellite imagery, day after day. Then the tremor and the hybrid activity kept showing the system was still pressurized. Then the ash emissions continued through the 9th and 10th of July, with the colour shifting toward black. Notice what that sequence is not. It is not a single, sharp event that spikes and then fades. the kind of thing you could file away as a one-off, and it is not random noise, a scatter of unrelated puffs with no direction. It is ordered. Each step follows from the one before it and sets up the one after. The alert was raised because the activity increased. The activity did not then subside to justify lowering it again. Instead, it persisted, and the satellite kept confirming ash, and the seismic record kept showing a pressurized system, and the emissions kept coming with the ash darkening toward black. When you can lay events end to end, and each one is consistent with a system that is staying energized rather than winding down, you are looking at a trend, and trends are what actually matter in volcano monitoring. A single big eruption tells you what happened. A trend tells you where things are heading. That is not one explosion followed by calm. That is a chain, each link tightening on the last, and that distinction between what the instruments can promise and what they cannot is the honest heart of this whole situation. They can tell us, with real confidence, that the volcano is erupting, that it is doing so frequently, that the seismic system is pressurized, and that the trend over the first 10 days of July has been toward more activity rather than less. That is a lot of genuine, actionable knowledge, and it is why the alert sits where it does. What they cannot do, at least not reliably, is give a coastal town a guaranteed warning before a flank lets go. The gap between those two capabilities is not a failure of the scientists. It is a limit of physics, of how a landslide behaves versus how an earthquake behaves, and of how little time a close-in source allows. Living inside that gap, knowing a great deal and yet not the one thing you would most want to know, is the uncomfortable reality of watching this particular volcano. The instruments cannot promise us they will catch a collapse before it happens, but they can tell us, very clearly, that the system generating that risk is currently active and currently escalating. And that brings us to the one question that all of this has been circling, the question that no instrument can answer yet. Part 14. The thing we cannot see. Yet. So where does that leave us, watching a small island in the Sunda Strait throw black ash into the sky, night after night, in the middle of July 2026? It leaves us with a volcano that is unmistakably awake and unmistakably escalating. 6 eruptions in under 10 hours. Ash darkening from white to grey to black. Seismic amplitudes climbing through a single morning. A system that hums with continuous tremor and never quite settles between blasts. An alert level raised to the second highest tier, and an exclusion zone widened from 2 kilometers to 3 because the people who know this volcano best judge the danger to have grown. None of that is speculation. All of it is measured, and it leaves us with a memory. December 2018. 437 people who felt no earthquake, heard no alarm and had no warning, because the wave that took them was not born from a fault, but from a piece of the mountain falling into the sea on an ordinary holiday night. That is the shadow standing behind every one of these eruptions, not the ash. The ash is only the volcano telling us it is energized. The real question lives in the island itself, in the loose new cone that is rebuilding, layer by layer, over deep water, on a steep slope, fed by a plate boundary that will never stop pushing magma upward. And I keep coming back to the strangeness of that arrangement. Everything that draws the eye in this story, the black columns, the amplitudes, the 6 eruptions before lunch, is the part of the danger that announces itself loudly. The part that actually killed people, the flank sliding into the sea, is the part that made no announcement at all. We are, in a sense, transfixed by the volcano's noise while the real threat sits in its silence. That is a very human failing, to watch the loud thing and miss the quiet one, and it is exactly the failing that a night in 2018 exploited. The whole discipline of watching this volcano well comes down to refusing to be hypnotized by the ash, and keeping at least one eye on the mountain's shape. Here is the thing we genuinely do not know, the thing no seismograph and no satellite can currently tell us. We do not know whether this rebuilding cone is stable enough to keep erupting without shedding a piece of itself into the sea, or whether the same silent no-earthquake pathway that opened in 2018 is being quietly reloaded, pulse by pulse, right now, in front of instruments that can see the smoke but cannot yet see inside the mountain. Lower risk than 2018, yes. 0 risk, no. And the gap between those two is exactly where the watching happens. It is a narrow, uncomfortable space to live in, but it is an honest one, and it is the only place from which you can see this volcano clearly, without either the blindfold of panic or the blindfold of denial. That is the discipline this kind of story demands. Not panic, because the current activity is not 1883 and it is not, on today's data, a confirmed imminent collapse. But not indifference either, because indifference is precisely what turned an ordinary night in 2018 into a catastrophe. The correct posture is the hardest one: sustained, patient, clear-eyed attention to a threat that may never fully announce itself. And that posture is not just for scientists. It is the right way for any of us to hold a story like this. Not to doom-scroll ourselves into terror over an eruption that may quiet down next week. Not to roll our eyes and dismiss it as just another volcano doing volcano things. But to understand what is actually happening, why it matters, what the real danger is and is not, and then to keep a calm, informed eye on it as it develops. That is what separates being informed from being either panicked or ignorant. The volcano does not need our fear, and it will not be helped by our indifference. It just needs to be watched, honestly and continuously, by people who understand what they are looking at. And this is not the only place on Earth right now where the ground is quietly doing something that our instruments can measure, but our warning systems may struggle to act on in time. Far across the Pacific, along a very different kind of subduction zone off the coast of the Pacific Northwest, another slab is under enormous accumulated stress, and researchers have been watching pieces of that system behave in ways that raise their own uncomfortable questions about how much warning any of us would really get. I mention it only to make a point that ties back to everything we have talked about tonight. All around the planet, the same fundamental drama is playing out in different forms. Slabs of the Earth's shell are grinding, diving, and locking. Pressure is building in places we can measure but cannot fully predict. And in more than one of those places, the most dangerous outcome is also the one that would give the least warning. The Pacific Northwest has its silent, accumulating strain on a locked megathrust. The Sunda Strait has its silent, accumulating instability on a rebuilding island cone. Different mechanisms, same unnerving theme, that the biggest threats are often the quietest right up until the moment they are not. But that is a story for another night. For now, the watch is here, in the Sunda Strait, on a child that grew up on the grave of a monster. So keep your eyes on the colour of the smoke, on the height of the columns, on whether that alert level holds at 3 or climbs toward 4. And ask yourself the one question that will decide whether the next few weeks are a footnote or a headline. When a volcano can send a wave with no warning, and the mountain making it is rebuilding itself right now over the same deep water that drowned 437 people once already, how many eruptions in a row does it take before watching quietly stops being enough?